get rotational work, we're going to start off with our same definition of work from before, where work is force times distance. In this case, because we're rotating, I'm going to replace that distance with an arc length, so delta S. And then, in kind of a weird move here, I'm going to multiply and divide by R. So basically multiply this whole thing by R over R, or basically just by 1, but it's going to create something good for us. So R times F and delta S over R. So it's R over R, so I've done nothing new to the equation. But what happens is I now have things in a good rotational format, right? Because R times F is torque, and delta S over R is theta. So work equals your torque times theta. To get rotational kinetic energy, we can start with our equation for work. Right? Remember, work was torque times theta. And remember that work was equal to a change in kinetic energy, so they're going to be similar things. Now, I'm going to change the form of torque to say that work equals my moment of inertia times alpha times theta, since remember, torque can be moment of inertia times alpha. And we're going to say that's equal to our change in kinetic energy from our work kinetic energy theorem. Now we're going to take kind of a random sidestep here and go over to our equation. Omega squared equals omega naught squared plus 2 alpha theta. And remember, that's just one of our rotational kinematics. But I have two similar values here in alpha theta and alpha theta. So I'm going to solve for that and say that alpha theta is equal to omega squared minus omega naught squared over 2. So work is equal to I times omega squared minus omega naught squared over 2. And we can kind of simplify this and write it in a form that maybe seems a little more familiar to us and say 1/2 I omega squared minus 1/2 I omega naught squared. And hopefully we see that that's pretty similar to 1/2 mv squared. Right? Remember, moment of inertia was kind of our rotational mass equivalent. Omega was kind of our rotational velocity equivalent. So in some ways, this is just the 1/2 mv squared, but for rotational motion. So our kinetic energy then, right, if work is our change in kinetic energy, just plain old kinetic energy, is 1/2 I omega squared. So now let's see how that form of kinetic energy factors into a problem. So maybe as just a real quick example, let's say we have something on a hill here, there's theta, it's up at some height, and we have a ball rolling down a hill. Now, if we take conservation of energy into account, let's say I want to know, how fast is it going down here? Might be a good problem. So taking conservation of energy into account, at the top we have gravitational potential energy, but that's it because it's not moving yet. When I get down to the bottom, I'm going to have kinetic energy because it is moving linearly in that direction, but it's also rotating at the same time. So we also have a rotational kinetic energy that needs to be factored in. So as we start to write this equation out, we'd have mgh for our potential energy, 1/2 mv squared for our kinetic energy, plus 1/2 I omega squared for the rotational part of it. And then, depending on what's given in the problem, we could solve for velocity and any of those other quantities. Now, notice these two things are kind of linear in nature, while this one's rotational. So it might help to do some substitutions here and make things either all rotational or all, maybe in this case, linear. Right? For example, it might help to do the substitution that omega is equal to v over r and plug that in for the omega. That way, you have everything in terms of velocities rather than omega and radians and things like that. So now we should be starting to see that just about everything we've done in a linear sense is also angular in nature. So the next one is angular momentum. So angular momentum, we use the variable L, capital L. Normal momentum, right, P was equal to mv. Well, my mass equivalent is moment of inertia. My velocity equivalent is angular velocity. So L is equal to I omega. Now, as with everything else, right, we could do conservation of energy with angular values with rotational values. Same thing with momentum. We can have conservation of angular momentum. It's also a conserved quantity. And so that means that my total L initial would equal my total L final. So for example, we could say I omega initial equals my I omega prime. Now notice here, I did put a prime also with this mass term. In past examples, it was just m stayed the same. Our moment of inertia here can actually change, right? Maybe a good example here is a figure skater spinning around. And if they're spinning around with their arms out, that's one moment of inertia, versus if they take their arms and tuck them in, now all of a sudden it's a different moment of inertia because this mass is distributed differently. And so you can actually change that. So, for example, when a figure skater's arms are out, they have a large value for I, and when they're in, it's a small value. So how does it compensate over here in terms of conservation of angular momentum? Well, if this value goes down, this value has to go up in order to conserve angular momentum. So what happens when a figure skater tucks their arms? They spin around a lot faster. Now, one tricky component of angular momentum is when we involve both linear and angular components. So let's say I have maybe a little disk here, and it's going to go and collide with something that's on a pivot point, and it's going to hit that pivot and then make it rotate. Right? That's a collision, so it's a great momentum problem. Right? We use momentum a lot for collisions. But this motion is linear, whereas this motion is rotational. And the way you do this is there's actually a way to do the linear moment or the angular momentum of an object that's moving in a linear fashion. The way we do that, right, angular momentum is I omega. And so what we're going to do is we're going to picture this object right here, right, because this moment before and after the collision are there's a very small difference in time there. And if you do a very small difference in time in rotational motion, it's approximately linear for just that little tiny period. So we're going to do the opposite and approximate this as rotational just for that little tiny instant right there. And if we do that, L equals, well, for a point mass, it's mr squared for I, and omega is v over r, so the r's are going to cancel. So L equals mrv for an object in a kind of linear fashion, but approximating it for angular. So in this situation, for the ball here, you'd use this for its angular momentum, and then you'd use the I omega for this for whatever its movement was there. So when we're working with both linear and rotational, you change the linear one to have a momentum of this rather than our normal mv, and then you can use conservation of angular momentum to solve. So it's kind of a very important problem-solving technique right there. Anytime something's moving in a linear fashion, but it's an overall angular problem because things are rotating, you use this for the linear object. So one important thing that we need to think about is the direction of three quantities, of omega, of angular momentum, and of torque, and how those directions relate to how the object is rotating. To do that, and to figure out which direction those things are pointing, we use something called the right-hand rule. So it looks something like this. So let's say we have an object that is rotating this way. Omega and angular momentum both point the same direction, which is up this way. And to figure that out, you use your right hand only and do something like this. You take your right hand, you curl your fingers in the direction of rotation and keep your thumb pointed up, or pointed away from your hand, and whichever direction your thumb is pointing is the direction of omega and L. So as long as you're curling your fingers in the direction of rotation, your thumb will always point whichever direction omega and L are. For torque, it's a very similar thing, using your right hand, keeping your thumb extended, but instead of curling your fingers in the direction of rotation, you point your fingers in the direction of the force applied. So sort of your hand points along R, your fingers point in the direction of the force, and whichever way your thumb is pointing is the direction that torque is. And so that's how we can think about direction in terms of whether something's positive or negative. You can call clockwise positive, counterclockwise negative, or something along those lines. Right, because we may have something that's spinning this direction, but is slowing down, which means the torque is going to be pointing down this way, even though L and omega are pointed that way. And so you can kind of see, yes, it's rotating this way, omega is that way, but torque is this way, so its velocity and the force are in opposite directions, so it's going to be slowing down, just like we're used to.